Imagine you have a microwave. You put your cold coffee in, press a few buttons, and a minute later, it's hot. You know what it does. You know how to operate it, but do you know how it actually works? Do you understand magnetrons and microwaves and how they excite water molecules? Probably not. For you, the microwave is a box, you put something in, and you get a result out. The process inside is a mystery. You trust it because it's simple, reliable, and the stakes are low. If it undercooks your food, you just put it in for another 30 seconds. Now imagine a different kind of box. This box is an AI. You give it a medical scan and it gives you a result cancer or no cancer. Or you give it a loan application and it spits out approved or denied. Or you give it all the data about a criminal defendant and it says high risk of reoffending. This is where the mystery stops being a simple curiosity and starts becoming a serious problem. This is the black box problem of AI. It's the gap between an AI's input and its output. It's our inability to fully understand why an AI made a particular decision. We can see the data that went in. We can see the answer that came out. But we can't clearly trace the path between the two. The internal logic is so complex, so tangled, that it's effectively opaque to human minds. It's a box, and its insides are dark. This isn't a problem with all AI. Simple AI is perfectly understandable. Think of a thermostat. If the temperature is below 70 degrees, turn on the heat. If it's above 70, turn it off. That's a simple set of rules. We wrote the rules so we know exactly why it does what it does. It's a transparent box, but the most powerful forms of AI today, especially those using what are called deep neural networks, don't work like that. We don't give them rules, we give them data. A lot of data. Think about how you'd build an AI to recognize cats in photos. You don't write code that says if it has pointy ears and whiskers and fur, then it is a cat. That would be impossible. A cat can be sleeping in a ball, hiding behind a sofa, or staring right at the camera. The rules would have millions of exceptions. Instead, you show the AI millions of pictures. You show it pictures of cats and label them cat. You show pictures of dogs, cars, and chairs and label them not a cat. The AI's neural network is a huge, interconnected web of digital neurons. During this training process, the AI adjusts the connections between these neurons over and over again. It tweaks tiny numerical values called weights and biases across millions of connections. It's trying to find a configuration that gets the right answer as often as possible. Eventually, it gets very, very good at identifying cats. It can spot a cat's ear poking out from behind a curtain with incredible accuracy. But if you ask it, how did you know that was a cat? It can't tell you. It can't point to a rule. The knowledge isn't stored in a way humans can read. It's distributed across that entire web of millions of tiny numerical adjustments. The logic is mathematical, not logical in a human sense. It's a pattern-matching machine of immense complexity. This process creates a black box. The very thing that makes the AI so powerful, its ability to learn subtle patterns from data on its own, is the same thing that makes it so opaque. We built the learning system, but we didn't build the final decision-making logic. The AI built that itself. So why does this matter? Who cares how the cat spotting AI works as long as it spots cats? For low-stakes tasks, we don't. If your phone misidentifies your friend in a photo, it's a funny mistake. If Netflix recommends a bad movie, you just watch something else. The consequences are trivial. But we are starting to use these black box AIs for things that are not trivial at all. We are outsourcing decisions that deeply affect human lives to systems we do not fully understand. And this is where the danger lies. Let's look at medicine. An AI is developed to detect early signs of diabetic retinopathy, a condition that can cause blindness, by looking at eye scans. Studies show it's more accurate than human radiologists. This sounds amazing. It could save the sight of millions. But what if the AI starts making mistakes? One study found that a similar AI system was performing brilliantly, but for the wrong reasons. It wasn't just looking at the eye, it was also picking up on the quality of the image, the type of camera used, or even tiny text artifacts in the corner of the scan. In short, it learned that scans taken with a newer, high-quality machine at a specialist clinic were less likely to show disease. It was making a correct prediction, but it wasn't based on medical pathology, it was based on a shortcut. It was a clever cheat. Without understanding why the AI is making its decisions, we can't catch these cheats. A doctor who gets a diagnosis from the AI can't ask it for its reasoning. They can't ask, what in this scan made you say that? They're just given an answer from a box. To trust that answer in a life or death situation, you need to know it's based on sound medical reasoning, not some random correlation in the data. What if a patient from a rural clinic, using an older machine, gets an inaccurate high-risk diagnosis simply because of the equipment used? The human cost of a decision made for the wrong reason is immense. Now, think about the world of finance. Banks are increasingly using AI to decide who gets a loan or a mortgage. You submit your application with your income, your credit score, your savings, and your job history. The AI sifts through it and thousands of other data points and comes back with a yes or no. If it says no, you have a right to ask why. Under laws like the Equal Credit Opportunity Act, a lender has to give you a reason. A human loan officer might say, your debt-to-income ratio is too high. That's a clear, understandable reason. You know what you need to work on. But what if a black box AI denies you? It can't give you a simple reason. The reason is a complex mathematical equation involving thousands of variables interacting in ways no human can articulate. Worse, the AI might have learned bias patterns from the historical data it was trained on. For decades, lending practices were discriminatory against certain races and neighborhoods. An AI trained on that data might not have a variable for race, but it might learn that people from a certain zip code or with a certain name or who shop at a particular store are less likely to repay their loans. It learns a proxy for the very biases we've been trying to eliminate. The AI isn't being malicious. It's just doing what it was told to do, find patterns that predict outcomes. It found a pattern that connects zip codes to default rates. But the result is the same. It's digital redlining, and because it's a black box, the bank can't easily audit it for this kind of bias. They might not even know it's happening. The person denied the loan is left with no explanation and no recourse, the victim of a decision-making process that is both inscrutable and unfair. The problem gets even more serious in the criminal justice system. In the United States, AI tools are used to help judges make decisions about bail and sentencing. These tools predict the likelihood that a defendant will commit another crime if released. A judge might see a score that labels a defendant high risk. This score can influence whether someone waits for their trial in jail or at home. It can influence the length of their prison sentence. But where does that score come from? It comes from a black box. The algorithms are often proprietary, owned by private companies who won't reveal their inner workings. But from what we do know, they use factors like age, employment history, and prior arrests. The problem is that factors like prior arrests are not neutral. A person from a heavily policed neighborhood is far more likely to have a record of arrests, even for minor offenses that were later dropped, than someone from a wealthy suburb. The AI, trained on this biased data, learns a simple, brutal lesson people from poor minority neighborhoods are high risk. It ends up punishing people for who they are and where they live, not just for what they've done. It reinforces and automates existing societal biases, but it does so under a veneer of objective technological authority. A judge sees a number spit out by a computer and might give it more weight than it deserves. When investigative journalists at ProPublica analyzed one of these widely used risk assessment tools, they found it was significantly more likely to falsely flag black defendants as future criminals than white defendants. Yet, because the system is a black box, it's incredibly difficult to challenge its logic in court or to hold its creators accountable. Perhaps the most visceral example of the black box problem is the self-driving car. An autonomous vehicle is packed with sensors, processing a constant stream of information about the world around it. Its AI has to make split-second decisions. Imagine a self-driving car is rounding a corner. Suddenly, a child runs into the road. The car's AI has to make a choice. It can swerve left into a wall, likely harming the passenger. It can swerve right into an elderly couple on the sidewalk. Or it can brake hard, potentially hitting the child. There is no right answer here. It's a horrible ethical dilemma. But the car has to do something. Its decision will be the result of the complex patterns it learned during its training. But who decided on those patterns? Did the programmers explicitly code a set of ethical rules? Almost certainly not. The car's ethics are an emergent property of its training, not a deliberate choice. After the inevitable accident, investigators will need to know why the car did what it did. Was it a bug, a sensor failure, or did the AI make a choice based on its programming? If we can't look inside the black box, we can't answer that question. We can't learn from the mistake to prevent it from happening again. We can't assign legal responsibility. Was it the car owner's fault? The manufacturer? The programmers? Without understanding the AI's reasoning, the concept of accountability starts to break down. We can't build a just and safe world with this technology if we don't know how it thinks. The black box problem is also creeping into our professional lives. Companies now use AI to screen resumes for job openings. With hundreds or thousands of applicants for a single position, an AI can quickly filter the pile down to a manageable number of top candidates. It seems efficient and objective, but what is the AI looking for? It was trained on the company's historical hiring data. It looks at the resumes of people who were hired in the past and who went on to be successful. It learns what a successful employee's resume looks like. Maybe it learns that employees who listed captain of the tennis team on their resume tended to get promoted. Or maybe it learns that the best performing software engineers all graduated from one of 5 elite universities. The AI will then start prioritizing new candidates who played college sports or went to those specific schools. It might also learn a negative correlation. Amazon once had to scrap a hiring AI because it learned to penalize resumes that contained the word women's, as in women's chess club captain. Because the company's historical data came from a male-dominated tech industry, the AI taught itself that male candidates were preferable. The AI isn't sexist. It's a pattern-matching machine. It found a pattern and followed it. But the result is discrimination. A qualified candidate might be rejected before a human ever sees their resume, for reasons that are hidden, biased, and have nothing to do with their ability to do the job. And like the loan applicant, they will never know why. It's important to be clear, a black box is not always a bad thing. As we said, for a Netflix recommendation, it's fine. The performance of the system is what matters most, and the consequences of an error are negligible. There's a constant trade-off in AI development between accuracy and interpretability. Often, the most complex, opaque black box models are the most accurate. A simpler, more transparent model might be easier to understand but make more mistakes. In some cases, we might be okay with that trade-off. If an AI model is 20% better at predicting hurricanes than any other model, we might use it to issue evacuation orders even if we don't fully understand its internal workings. The benefit of its superior accuracy saving lives outweighs the need for a perfect explanation. We can test its performance rigorously, and if it proves reliable over time, we can learn to trust its outputs even without understanding its process. It's similar to how we trust a seasoned pilot's intuition. We might not understand the exact subconscious cues they are picking up on, but we trust their track record. But for areas like justice, finance, and medicine, where individual rights and well-being are on the line, and where historical data is riddled with bias, accuracy is not enough. We need fairness. We need accountability. We need to know why. The good news is that this problem is not being ignored. An entire field of research has emerged to tackle it, called explainable AI, or XAI. The goal of XAI isn't necessarily to make the entire neural network perfectly transparent. For a model with billions of connections, that might be fundamentally impossible. Instead, the goal is to build tools that help us peek inside the box and get a better sense of what's going on. It's like giving a mechanic a diagnostic tool for a modern car engine. They might not understand every single line of code in the engine's computer, but the tool can tell them which sensor is failing and why the engine is misfiring. One popular XAI technique is about measuring feature importance. This method tries to figure out which pieces of input data were most influential in a single decision. For a loan application that was denied, a feature importance tool might tell you the top 3 factors were debt-to-income ratio 45%, length of credit history 20%, and recent credit inquiries 15%. This is a huge step up from just getting a no. It provides a human understandable reason for the outcome. Another set of techniques tries to create a simpler approximate model to explain a local decision. One is called LIME, which stands for Local Interpretable Model Agnostic Explanations. The idea behind LIME is clever. It says, okay, the global black box model is way too complex to understand, but what if we just try to explain this one single prediction? LIME essentially takes a single data point, where your loan application, for example, and creates a tiny, simple, transparent model that mimics how the big black box behaves right around that specific point. It's like asking, I know the tax code is thousands of pages long, but for a person with my exact income and deductions, what's the simple rule of thumb? It provides a local explanation, not a global one, but that's often exactly what you need. A different approach, called SHAP, comes from game theory. It treats the AI's prediction as a team game. Each input feature, your income, your age, your credit score, is a player on the team. SHAP calculates how much each player contributed to the final outcome. It can tell you not just that your income was important, but that your specific income level pushed the prediction 10% higher, while your number of credit cards pushed it 5% lower. This gives a much more detailed and nuanced picture of how the decision was formed. There are also methods that generate counterfactual explanations. These answer the question, what is the smallest change I could make to get a different outcome? For a loan denial, a counterfactual might be if your savings account had been $2,000 larger, your loan would have been approved. This is incredibly powerful. It's direct, actionable feedback. It turns a frustrating rejection into a clear goal. It gives people agency. These XAI tools are not a magic wand. They provide approximations and interpretations, not absolute ground truth. But they represent a critical shift in focus. They acknowledge that building an AI that is merely accurate is not good enough. We also have to build tools for understanding, auditing, and questioning that AI. The black box problem is not just a technical challenge. It is a human one. It's about trust. How can we trust systems to make fair and safe decisions when we don't know how they reason? It's about accountability. When an AI system harms someone, who is responsible? And it's about our own role in a world increasingly managed by algorithms. As AI becomes more integrated into the fabric of our society, we cannot afford to have critical parts of it be unknowable. We need laws and regulations that demand a certain level of transparency for high-stakes AI systems. Europe's GDPR legislation already includes a scholar right to explanation, giving people the right to be told the logic behind an automated decision that affects them. This is a step in the right direction, creating a legal incentive for companies to move away from purely black box systems. We also need to remember that AI should be a tool, not an oracle. In critical fields, the final decision should always rest with a human. An AI can be a powerful co-pilot for a doctor, pointing out things in a scan that a human might miss. It can be a useful assistant for a judge, organizing case files and summarizing evidence. But the human expert, with their domain knowledge, common sense, and ethical judgment, must remain in the driver's seat. They need to be able to question the AI's recommendation, understand its basis, and override it when necessary. The black box problem is a reflection of the incredible power of modern AI. We have succeeded in building machines that can learn in a way that is alien to our own minds. They don't think in terms of rules or logic, but in terms of high-dimensional mathematical patterns. This is both their strength and their greatest risk. The challenge ahead is not to stop building these powerful systems. The challenge is to build them responsibly. It's about building the tools for explanation, right alongside the tools for prediction. It's about ensuring that as our machines get smarter, we don't lose our own understanding of the world they are helping us shape. We need to be able to open the box, at least a little, and let some light in.